Hello, good morning. Okay, this is my third video, I think. Okay, let me just give a recap of what we have done so far. We started with a new series on tension. So tension is not equal in connected bodies. This was the first video actually, which is saw across here. And then we looked at the next one, which is tension is not equal at different positions in the pendulum. Okay, so we saw one of the simple pendulum, and then here you observed that the tension is given by mg cos theta at static positions. Remember, this is not the what do you call the pendulum in swing. And then as a result of this, then I described when this will be equal. Okay, I am discussing both the cases. When can tension be equal? When tension cannot be equal. If you remember the previous case also here, you see when can tension be a constant? When tension cannot be a constant. Okay, both I am discussing. Okay, in a similar way, this also we looked at. So tension will be a constant in case of the conical pendulum, as you see. So it experiences the same weight throughout its plane. So that's what we have seen. Now let us look at tension is not equal. Okay, so I am back. So we had looked at conical motion, conical circular motion. Then the question that arises to me is it that the tension is always constant in a circular motion, or does the tension change even in different circular motions? Towards it, I looked at tension is not equal in vertical circular motion. There's one more misconception. Okay, let us look at this as why it is not equal. Tension is not equal in vertical circular motion. Now, what happens is in a pendulum, let me just recall. In a pendulum, this is my tension, this is my mg cos theta, because this is my angle theta, this is my angle theta. So this is what we get. This is in case of a simple pendulum. And there I wrote something as static condition. What is static? That means at a point of time, at a moment, at an instant, I just find out what is the tension. This is what we did. The second condition we looked at is the same pendulum, instead of oscillating like this, it's moving in a circle like this. Moving in a circle like this. So as it is moving like this, it describes an angle theta. And every time the tension here is always equal to mg cos theta. This is conical pendulum. Whether the position of the bob is at this point, this point, this point, this point, wherever it is, you observe that the tension is always same. Now, what many of them had thought is that if it is only an arc of a circle, it could be tension is varying. And if it is one full circle, the tension remains a constant. When I described this in my class, that's what people thought. Students thought. And finally, when I asked a question in vertical circular motion, they just consider that tension is remaining the same. Now, this comes to a concept question asking that when should I apply tension to be a constant and when I should not, right? So that's what I had taken this example. Now, towards it, now let us consider a circle, a vertical circle as shown here. When the pendulum is at this point and it is also moving, now the tension acting here is T here, and this is your mg. Okay, so therefore, now what happens here? You can see, let me call this a tension as T1. Now this T1 minus mg should be equal to mv square by r. Right? Naya concept. How did you get this? We did not use it here. We did not use it here. But all of a sudden you are getting it. Right? Everyone has this question. When it comes to vertical circular motion, everyone has this problem. Okay, suddenly you are introducing something. From every class, you are putting across some new concept, new equations. How do you put it? Okay, now let me tell you. Whenever a particle moves in a circle, the first thing that you would know is the driving force should be equal to the centripetal force. Okay, if there has to be a circular motion, then the driving force should be equal to your centripetal force. Then you might have a question by now asking, where did you do this? See, there's a circular motion here, right? Where did you do it? I didn't do it. The reason is because, see, if I have to do it, then it will be for a different task altogether. Now, this is your tension T here. I am now looking at a conical pendulum. This is your tension T here. So the component of this tension along this direction should have been T cos of 90 minus theta right? This is my 90 minus theta. So therefore, T cos of my 90 minus theta, which should be T sine theta. Now this is your driving force. Okay, the driving force is T sine theta. Thus I should have written T sine theta is equal to mv square divided by r, where r is the radius of the circle, v is the speed. This would really make sense. Here also we are supposed to do it. But the part of the derivation that I am doing here does not need this. So as a result of it, I didn't do it. Is this clear? Okay. Now here in a vertical circle, what happens? You have T1 here, you have mg here. The difference between these two is equal to mv square by r. So therefore, I can now write T1 should be equal to mv square divided by r plus mg. Let me call this as equation 1. Let me consider one more position. This position. This position, what are the forces acting here? There is a tension acting here. Let me call this T2. I am not going to call it as T1. Reason is because I know very well that tension T1 and T2 are not going to be the same. Let me prove it first. Okay, then I will call this. Okay, so therefore, let us say this is tension T2. What are the force acting here? mg is acting here. Is there any other force acting here? No. So therefore, now we have only T2 is equal to mv square by r. But why mv square by r? Because it's moving in a circle. Whenever something is moving in a circle, definitely one side of it is mv square by r, the other side is net force. Why should it move in a circle? Why should it move? Tension is pulling it like this, right? So therefore, tension equal to mv square by r. Now you see, definitely compare with these two equations. If this v is one and the same, even then you see this mg factor is missing. So definitely this tension is different from here. Let us consider this point. Okay. At this point, you see mg is acting downwards. Okay. Then there's a string which is connected to it. This object is always pulled downwards, right? So therefore, this is T3. Let me call this T3. So thus you should write T3 plus mg is equal to mv square by r. Okay, this is a net force. I already written. This T3 should be equal to mv square by r minus mg. Call this equation number 3. Now what has happened? Here you see mv square by r plus mg. Here this mg is missing. Now you are subtracting it. Wow, that's great, right? You see how systematically, how nicely the pattern has been shown. So therefore, now as the particle keeps on going, tension is reducing. When it comes back, you will observe, don't say that this should be minus 2 mg. Okay, so it will not happen because it's repeating the cycle of events. So when it comes here, let me call this as T4. Now mg is once again here. So T4 should be equal to mv square divided by r only, because mg does not contribute. It's perpendicular here, right? So it does not contribute. So thus you see T2 and T4 are equal, while T3 and T1 are different, right? So while the particle is going upwards, the tension keeps on reducing, right? The pulling force keeps on reducing. When it goes to topmost position, tension almost reduces, right? See, the tension almost reduces. T3 here. This is T3. At this point, almost it's reducing. But when it returns back on this return back journey, then once again, this from the minimum value, it keeps on increasing until it reaches over here. Thus, at every point you take, the tension is not going to be a same or constant in a vertical circular motion. I hope this is clear. While in a conical motion, definitely the tension will be the same everywhere. But in a vertical circular motion, tension is not going to be the same. Thank you, friends, for watching. The next video, we'll see some more on tension. So this is nothing but the overall way as how the tensions can be presented in the form of a circle. So that's what has been shown over here. Okay, thank you. So if you like this video, do like, share, comment, and subscribe to my channel for further updates. Thank you.